Okay, so let's start the new topic of this week. Okay, we are going to talk about a new group of the things in the Chomsky hierarchy. If you remember, we used to start from. Let me have something here. Let me put something underneath of my laptop. Much better in terms of height and cooling, everything. Okay, so if you remember in the higher Chomsky hierarchy, we had four different four different groups for the computations and machines. We started from type 3, the smallest part, which was the regular languages, machines, and grammars, and the machine which was related to that was finite automata, if you remember, we discussed that, and then a bigger and larger group of the machine, which was push-down automata, and the language and grammar for that was text independent, context free, let's say, languages and grammars. And now for today, we are going to talk about a bigger group, which the other two groups we talked about previously, they are kind of the subset of this group. This group is called they belong to type 1 of the Chomsky hierarchy. The machine that we use for that is called Turing machine. We are going to talk about this kind of languages and machines today. And if you remember, when we talked about that hierarchy in the Chomsky hierarchy, we said whatever you go toward the from type 3 to type 0, the machine gets more powerful and you will have more capability, etc. And there was kind of a subset story. I mean, the thing you could generate with the type 3 grammars and languages and machines, obviously finite automata, it would be possible that that would belong to the type 2, and then the stuffs of type 3 and 2 could belong to type 1, but the other way around is not correct. I mean, the thing that you can generate with type 1, like the Turing machine, it doesn't mean necessarily you are capable of doing the same thing with the push down automatas, PDAs, and also with the finite automatas, etc. That was a summary of what we have talked for the last few weeks. For today, like I said, we want to talk about the type 1 stuffs. The machine that we use for that is the Turing machine. So that's the whole story. If you remember, the machine by far we have reviewed, they have been the finite automata, which was like that. And then we went through the push-down automata, something like that. The difference was very similar to finite automata, but the difference was we had a new component which was called stack, and we have the capability to push something into that and pop something off of that. That means, and the logic for that was last in first out. Whatever you push the last time, which was B, you could pop it off for the first time when you wanted to pop something from the stack. Okay, and that was head. That was called head. That was the state of the machine, and that was that was called tape. That was the state of the machine, and that used to be called as the head of machine. Machine used to read a character from the tape. It was on a string, specific string. That was very similar in both cases. In this case also we had the stack. But that's the Turing machine. In Turing machine we have some differences. So like I said, finite automata are the simplest machine, capable of accepting an infinite set of strings. You could have any kind of string in here, machine with a specific number of states, and the head of machine could read from the string, and we had a criteria for accepting or rejecting the string of a specific language. If that string is accepted by the machine, that means that's a string of a specific language. Push-down automaton can carry out computation beyond the capability of finite automata. You remember it was a little bit more powerful language machine, and we talk about what does it mean more powerful machine. More powerful machine means it can accept more languages. It can accept the languages that are not accepted and generated by finite automata machines. Okay, So that's the meaning of the more powerful. It's not the meaning of the memory stuff, etc. Of course, memory stack and something like that, they are the means to make a machine more powerful, but the powerful by itself doesn't mean this stuff means, but it means having the capability of to working on different languages. Okay. At the other end of the scale of computing power is the Turing machine. And the Turing machine is the machine which was called Turing after the name of English mathematician Alan Turing, who devised. And we will talk about the Turing. He has been an interesting guy, English interesting guy, and we will go through his life and what he has done. That's an interesting story. Okay, Turing machines can carry out any set of operation which could reasonably be called a computation. That's something in new term. We will see what does it mean in the coming slides. Actually, when we talk a Turing machine, that's not just the matter of generating a string of the language. That's kind of doing a computation. So see, slowly we are getting closer to the computability and computation. So in Turing machine, we have a tape very similar to other machines. Okay, we have like previous automated classes, a Turing machine can be visualized as having a control box, which at any point is one of the finite state numbers. So we have the states. That's a box which shows, that's a control box which shows in which state we are. An input tape, we have a tape that we have a number of characters of the alphabet over that. Okay, so we have squares, and in each square we have a specific character, very similar to other languages, like I said, and reading head. We have a reading head. That head starts to read the stuffs and move toward the right and so on. Okay, well, we have some differences in here in the Turing machine in comparison to the other machine. If you look at the shape of the Turing machine and compare it with the others, you can see what is the difference. One of the differences, at least, is obvious. The first obvious difference is the tape is infinite. I mean, it's not like the finite automata or push-down automata, which tape is finite, and you have specific capacity for the specific capacity, a specific number of boxes in here, or you have infinite number of boxes in here available. So that's one of the differences. So besides reading from the input tape, as the other automata could do, a Turing machine can also do. So that's one of the main differences. It can write. In the other machines, we used to read the character, move to write, change the state, read another one, move to right, change the state, and so on. That was the same for the push-down automata too, right? But in the Turing machine, apart from reading, we can write a character on the tape, and that makes machine a little bit more powerful. And also we can move. We have two options for the move. We can move left or we can move right. In these two machines, we had only one choice. We could only move toward the right. But in this case, we can move to the left and to the right. And like I said, the length of the tape, the length of the tape and number of squares in here are infinite. That's another difference in here, right? So a Turing machine computation is assumed to begin an initial state Q0. As usual, we used to start from initial state Q0 with the reading head over the leftmost symbol of the input string. So that's very similar to other machines. We are in the initial state Q0. We are on the first character of the string. The difference is we could have some other stuffs before in the left side of the initial character. So assume that the tape extends infinitely to the left and right. Like I said, the length of the tape is infinite. So you can move to the left and right whatever you want. And the other difference, all tape square not occupied by symbol of input string are filled by a special blank symbol. So in here, that's another difference. So you have the string you want to deal with, and the length of the tape is infinite. But what about the other squares, other elements of the tape? They are filled with the blank symbol. Nothing is in there. But we call it, we show it with the hash symbol, and it's called blank. Okay, so let's review. What was the differences? The tape length is infinite, the first one. We could have blank symbols in here before and after the string we have. We can move toward the right and left, both direction, it is okay. We can move whatever move we want, that's okay, no restriction in here. And also we can write to the string apart from reading from the string. So they are the differences between the Turing machine and the two other machines we already discussed. And as you can see, whatever we go to the left, we get to the simplest machine gets simpler. So less power we will have for the machine will provide us with. And whatever we go to the right in this course of the machines, we will get to more power and machine gets more complex. Right? Okay, so let's move on. So what is the whole story of the changes of the states? You remember in the machines we had kind of a transfer functions. You could say if you are in state Q0, if you see a string character symbol A, and then what would happen? What would happen on the tape and what would happen on the states? That would be something similar in the Turing machines then. So it is called instructions. Well, we showed the instruction in this compact form, like something like that. We are in state Qi, we see symbol AJ, and then we will go to a new state Qx, and something X happens. What does this X mean? So Qi and Qk are states, and Qj is the AJ is a symbol of the alphabet. Okay, X is either an alphabet symbol or one of the special symbols left or right. So we have, that's a kind of compact version of representation. So if you are in state Qi, you receive a J on the head of machine, okay, and then you will go to a new state K, QK, and then what would happen? X. What does it mean? If X is a symbol, that means we will do something, or if X is L or I, that means L or R, that means something different. To apply an instruction, the Turing machine must be in state Qi, scanning AJ on the input tape. Then, depending on the value of X, the instruction works as follows. If X is L or R, then AJ is left unchanged, so we don't change the tape content. If it is L or R, capital L, capital R, we will leave it unchanged, and then we will move toward the left or right up to the value of X. If it is L, we will go to left. If it is R, we will go to right. So that means that's the whole story. If X is L or right, L left or right, we will leave it unchanged, just we will do a move. If X is a symbol of the alphabet, then the symbol only changes and we don't move. Okay, so from here we can see if we have any changes in the state. From here we can see if we have left it unchanged and stay there and move, or we have changed it and don't move. So we have two cases. Once an instruction is applied, the Turing machine enters state Qk as with simpler automata. Okay, so that's the Turing machine example. We have the status Q0, Q1, we have the alphabet A, B, and like I said, the blank. Here we have blank also. We have an initial state Q0, and we have some instructions, right? So in instruction for here, for example, it says, if you are in Q0, you receive A, you will go to Q1, and you change A to B. What does it mean? It means we change the things on the tape, and we don't move because we don't have any L or R in here. In this instruction, we will move from state Q0 to Q1. We will change B to A, and we don't move on the head. In this one, we will replace blank with blank. Actually, we do nothing, but we change the state from Q0 to Q1. The state from Q1 to Q0, don't change the tape content, keep it as A, and move toward the right. Change from Q1 to Q0, don't change B on the tape, and move toward the right. So that's a very simple example Turing machine in here we discussed, right? Okay, so can you see any other differences in here? I'll ask this question and please type me on the chat. Do you see any differences between the any other differences between finite automata and push-to automata and the Turing machine in here? Please type me on the chat. Do you see anything I have missed which we used to do for the other machines? Any idea? Do you have any idea in here? What we have missed, what we used to talk about previously, but we don't talk about now? Any answer? What we have missed in here? Any idea? No idea? Let me provide you with a hint. That's related to the states. Do you see anything which we have not talked about the Turing machine in here? In defining a machine? Now, any idea? Nothing? Can you hear me at all? I hope you hear me. No final state. Very good, Vincent. Exactly. We don't have any final state here. We have not talked about the final state. So that's the other difference we are facing in here. So the Turing machines will deal with the deterministic. So if that's kind of a deterministic Turing machine, which would be similar to the definition we had for the deterministic for the other two types of machine, here for each state and each alphabet symbol, there is at most how many possible moves? Any idea? Any thought? Do you think how many moves we can have in here if that's deterministic? So in the Turing machine, if that's a Turing deterministic Turing machine, how many possible moves we can have in a specific situation? Obviously, it should be just only one move. Why? Because if that's deterministic, that means you should have only one option. Everything is deterministic, right? Okay. So as with simpler automata, a Turing machine can reach the end of the input, for example, ABA above. Unlike, so you remember one of the mission of the main mission, let's say, the finite automata and push-down automata machines was to see uh, if the string is accepted or rejected. If the string of a language is accepted by machine or rejected. At that time, if you remember, we used to finish at some stage. So unlike finite state automata and push-down automata, a Turing machine can read and write the blank symbol. So that means if you are in here, we read and move right. This means it can extend its computation into portion of the tape beyond that originally occupied. So that's our string. We'll start from the first symbol with the state Q0, and then we do a lot of couple of computation, and then we may get to specific location which is only blank. That's interesting. So one possibility open to Turing machine is that it might compute forever, since the length of the tape is infinite, and that means we can move toward the right and left, and that means, and also we can write and read the blank. So that means easily we can get to the area with only the blanks, and that means we can compute forever. It means never it is finished. So that something can happen in the Turing machine, but it didn't happen in the the two other machines we had. Okay, this is an important property of the Turing machine. So with the two other machine, the computation halted when two circumstances we had, we could halt the computation and we could finish the story of doing the things in the machine. The first thing was we reached the end of the input string. Whenever we get to the end of the string, the machine is finished the computation, and also no instruction could be applied. If you are somewhere in here, if you are in a specific state and there is no instruction to say if we are in this state and we see these symbols, what should we do? If these two things happen, we used to halt the computation in these two guys. Okay, since we don't have a halt when the end of the input string is reached. Why? Because we said we can write and read the blank and we can continue forever. So it doesn't mean necessarily we can halt the computation whenever we get to the end. Is reached with the TM, and only so the only option B could be the case the computation is halted. So in Turing machine, then computation is halted, then we have no instruction could be applied actually. If a Turing machine reaches a point in its computation at which no instruction is applicable, then machine stops computation and it halts, right? So that's another difference. We also do not need to have a designated set of finite state for Turing machine to know if a string should be accepted or rejected. So we don't have any finite state. If you remember again, previously we used to say a string is accepted if we finish the input string and also we are in the final state. While here in Turing machine, we don't have any final state. So that's not the criteria to say if we accept or reject an string. Turing machine is string acceptance. When an input string is given to a Turing machine in standard starting configuration, if the Turing machine halts after a finite number of moves, the string is accepted. So that's the only criteria. If you have a specific string and if it is halted after a finite number of moves, then that means the string is accepted. While previously we used to say you accept the string if you finish the whole string and if at that time you are at the finite state. But here we don't have it. If after a finite number of moves you are stopped, halted, then the string is accepted. Otherwise, the input string is rejected. That means an input string is said to be rejected with the Turing machine never halts, right? So let's back to example one. I have a machine with these two states. We have the alphabet, this alphabet, initial state, and this regulation. So let's see what happens. So we have some blanks in here, in the left side of the starting symbol. We have the string in here, and then some other blanks. I am in Q0, so what happens? In Q0, seeing A, so that's rule 1. So what happened using the rule 1? It says you should go to Q1 and replace A with B. Okay, I have replaced A with B. See, it was A. I have replaced that with B. I have changed Q0 to Q1 and I didn't move. Why? Because the X in here is not R or right or left. It is only a symbol. So that means I just write the symbol. See, I have read the symbol A and instead I have written the symbol B instead of that. So what happened then? I'm in state Q1 and CB. I'm in Q1 and CB. I should go to Q0 and move R. So I change the state to Q0. I move one right. So the head of machine would be on B. I'm again in Q0 and B, Q0 and B. What would happen? Q1 and A. So I change to QI. I write A instead of B. So that would be A. So then Q1A, that's here, Q0 right. So it would be Q0 and I move right toward the A. So I'm in here then, Q0. So then again rule 1, I will get in here. Then rule 5, I will get to here. Let's check the rule 5. I'm Q1 and I will see B. Q1, B. I will go to Q0 right. Q0 right. Then I see blank. I'm in Q0 and C blank. I am in Q0 and C blank. I will go to Q1 and don't change it. I mean override the blank. So I will go to Q1, don't move, and I stay in the blank. So then Q1 blank. As you can see, there is no instruction in here which tell us if I'm in Q1 and see blank, what should I do? So I halt. So the string is accepted. So this machine accept this string, as you can see. And finally, if you look at the string you have on the tape, it is different from what you had in the beginning. The string was ABA and the string here is BAB. What does it mean? It means, if you remember, I said in Turing machine we can go beyond accepting or generating the strings. It can do computation, and changes that we apply on the string, input string, at the end of the day is kind of the computation. If you receive something and generate something, that's the meaning of computation. That's the meaning of the functionality. What does it mean, the function? Function means it can receive something in the input, x, and f of x is y. That's the output. Y could be different from the input. That has happened exactly in here, and that's why we say Turing machine can do computation for us, right? So Turing States, Turing machine example. Okay, we have the same machine kind of. This machine scans and input a string from left to right, changing A's to B's and B's to A's until it encounters the first blank. Then it rewrites blank to the as a blank, changes state Q1. That's the definition of that's the explanation of what we did in here. Okay, example 2. Let's add another rule to the example to see what happens. We were somewhere by here. Okay, that's the same. I'm in Q1, I receive B. I'm in Q1, I receive B. I will go to Q0, move right. I will go to Q0, move right, which is blank. I'm in Q0, receive blank. I'm Q0, receive blank. I go to Q1, stay there with blank. Q1, stay there with blank. Now I have added this rule. I'm in Q1, receive blank. I will go Q1, stay Q1, move right. Stay Q1, move right. So that's rule 6. That's the same rule again, rule 6. So see, whatever I do, I'm just moving on the blank, 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 blank. Can you tell me when the machine will stop computation and it halts? It never. It never can halt. It continuously continues uh, actually computation. So it never halts. So the question is, if this machine accept this language, this string, no, it cannot accept because it never halts, right? So let's change this regulation. Let's change Q1 to Q1 and this guy, and don't move. Okay, we don't move to the right, but we write the blank again. So if we are in here, we stay there, we don't change the blank. Stay there, we don't. Although we don't move toward the right, but it's not in a situation the machine stops and halts. Machine continues staying there and changing the state to Q1, Q1, Q1 forever. So the machine doesn't halt, won't halt. Okay, so this string is not accepted by this Turing machine too because it's never stops. The Turing machine M is defined by this quadruple. Okay, so you have the number of states, you have the alphabet containing the blank, you have the initial state, and you have a partial function from K to sigma. That means the instructions we had, the rules. We will have some rules. So that's the definition. Like I said, in some cases they say we define the machine with 7 different elements. So like the alphabet, blah blah stuff, etc. in here. But it doesn't matter. So that's 2 different conventions. We follow this convention in this course. The Turing machine M accept the language L if M accept all the string in the language and rejects all the string which don't belong to that language. That's the same thing we discussed in the finite automata and the push-down automata. A language is Turing acceptable if there is some Turing machine which accepts it. That's exactly the same. Okay, what is the situation? Maybe if you want to analyze the machine and see how machine goes through the symbols of my string, etc., it's little bit more, it takes a lot of time to plot a lot of things, etc. So is there any easier way to do that? Yes, that's the matter of situation. A situation is exactly one of these states, one of these stuffs. That's a situation, a situation, a situation, and so on. So a situation is we are in a specific state, we receive a symbol and we do something. So that could be something like that. Let's rephrase all these graphs, state diagrams, kind of, to these situations. The first time the situation is we have kind of the empty in the left hand side, left string, which is empty. Then I'm in a specific string. Then what is on the head of the machine? A. And what is on the right side of the head? That's BA. So left string, current state, current input tape symbol, and right string, right? So that's the situation. What's the situation of this guy? It could be again empty. I'm in state Q1, head of B, head is B, and I have BA on the right side. And then when I'm going here, left side is B, I'm in Q0, I see B, and right side is only A. So if you want to analyze the machine like that, you don't need necessarily to plot all these guys. You can just write the iterations. and the situation will tell you what is the whole story, what will happen exactly. Let me see if there's any chat question. No. Okay, let's continue. Okay, so, and it could be something like that. We can plot it with the state diagram also, apart from the thing. So it could be something like that. We can say if I'm in state Q0, if I receive B, I will move to right because I have R in here, and I will keep B as it is. So I will keep B and I will move right. If I'm in Q0, receive A, Q0 receive A, that means I will move to Q1, and that means I will move to right, and also that means I will keep A. Okay, so that's a state diagram again for instructions. We can talk about the things using the state diagram. So question, what state is possible to halt in this machine? Is it possible to machine halt somewhere? Only state Q1. In this state, we won't halt. Why? Because if we are in this state and we receive blank, we will move right. We will see another blank. We will state in Q0. Again, we will continue computing on this state. So it's never would happen halting in this state. Only in Q1 it can happen. We can halt in here. So for example, if we see blank in Q1, there is no instruction, we can halt in here. But if we receive Q1 and receive A, we can move right. If you receive Q1 and receive B, move right. And that's okay, because whatever we move right with seeing A and B, I see A move right, I see B move right, and all the time I stay in Q1. Finally, I will get to a blank at some stage, right? And then there is no regulation to say if I'm in a state Q1 and I receive blank, what should I do? So that means I will halt in here. So this machine can halt in state Q1, but it never can halt in state Q0 if it faults something. So how this machine will reject something then? Something like that. So since you only halt in state Q1, that means at some stage you should move from Q1 to Q0 to Q1. And how you move from Q0 to Q1? When actually you receive an input string of A. In this string, I never see any A. So that's everything B. So that means I'm in state Q0, I receive B 3 times, I stay in this loop, and then as soon as I see blank, I will get into here, and then for infinite number of times, I will move in this loop and never it halts. So that means this machine cannot accept this string. So that's another way of analyzing if the machine can accept the string or not. You can write the situation, you can plot these guys, or you can analyze from these things and just write down what will happen. Okay, what this string and this machine, that's the same machine. We have shown that in here. Okay, and that's the string. So situation, that's an empty in the left hand side. We are in state Q0, we receive A, and in the right side is BA, the star. And then according to that, we are in Q0, we receive A, that means we will go to state Q1. So, and then we will move right. So that means A from here move right. We are in state Q1, and out of the BA I will have B. Okay, and I will write B. I will have B on the front of that BA guy. Will break them into B and A. This A goes in here. The state will go to Q1. Why A goes in here? Because actually we move to right. And what about the BA? B goes to the top of the head, and we will left A. And then what will happen? I'm Q1, I receive B. Q1 receive B, I will move right. So B will jump in here, A jump to the head, there is nothing, it would be empty. I'm in Q1, I receive A. Okay, and then I will move right. So A will move right, that means I will move right, A move left behind the state. I will state in Q1, and that would be blank and nothing, and empty in the right side. Okay, so that means let's check if there's any question. Chat, no question. Okay, so that means the string is accepted by this machine. And when we talk about this guy, like we said, we are instead, we have empty, we are in Q0, we have B on the head, and that's B on the right side. So in Q0, if you follow that, you will see the string is rejected. Why? Because exactly that's this situation. We receive the B's, we won't change the state from Q0 to Q1, and in Q0 all the time, if you get to the blank, you will stay there forever. So that's the reason why BBB is rejected by this Turing machine. Okay. Turing accepting languages. The above Turing machine accepts all the strings in A, B star, which contain at least one A. Why? Because like we said, you should have at least one A to guarantee at some stage you move from Q0 to Q1. Because if you stay in Q0 forever, you will finally get into this infinite loop, and that would be crazy. You never halt and the string is rejected. So at least you need to have one A. So what does it mean? So any string of A and B, even nothing, and at least one A. So it could be A, B, B, A, B, 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 A, B, 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 whatever. At least you need to have one A. Whatever string can be accepted by this guy. It scan left to right and stay in Q0 as long as this is it seems B's. As long as it seems B, it will stay in Q0. Once it sees an A, it goes to Q1 and continues rightward until it gets to the blank. Then it halts. If it meets the first blank in state Q0, however, it scans right forever, rejecting all the strings and without going to do the stuff we talk about. Okay, Turing acceptable and decidable languages. We have seen already that some languages are Turing acceptable. Okay, there is some Turing machine which accept all the string in L and rejects all the string not in L. Some languages are okay. We can apply some changes to this strategy. We can slightly different but very related. The idea is that of Turing decidability. That's different from being accepted by the machine. If we designate a set of final, what? Something new happen. If we design a set of final states to some Turing machine, if all the string in a given language L halts in the final state, if X is in the left hand and non-final state, if X in the non is not in the language, then L is a Turing decidable. So by adding the final state, we can say if the machine stays on the final state when the string is finished, so that means machine is decidable. Otherwise, machine is not decidable. So that's something beyond it. And partial function, what does it mean? Recall from mathematics theory that a partial function generalize the definition of a function by not forcing up. So you mean, what does it mean, the partial function? Partial function in mathematics is a function that not necessarily brings everything from the domain to the board. So if you have all these things in the domain, only the function is defined on a set of the values on the domain of the function. That's called the partial function. It could be applied to the Turing. If you remember, we said in Turing machine, we can do a little bit more computation than just accepting or rejecting the strings. So partial recursive function. Turing machines are probably most often viewed not as a language acceptor, but as a device which computes functions. That gets interesting. We are going toward the computers, right? The initial input string is the argument to the function, and the expression on the tape when the machine halts is taking the value of the function. If you remember, I said that exactly. I said if you start from this guy, that's the input of the function. If you finish at here, that could be the output of the function. And that's the reason why we say the machine could be kind of a function, computing a function. Okay, so state K alphabet. Imagine this machine. The above example compute the function AB whatever to AB whatever such that when FUV, V is the input and U would be the input and V would be the output, and what is applied to that string? That string is actually changing A to B to get to a new values. If the TM does not halt for a certain input, that means the function is not defined for that argument. That's the partial function. Partial function may not be defined for some input values. So that's the story of the Turing machine when we look at that as a computer. Okay, so if for a specific input U, machine is not halted, so that means that Turing machine is not defined for that specific input value as the function. That's very interesting, isn't it? So maybe the question could be, I will give you a string and say, can we compute the value of the output, value of the function for this specific input using this Turing machine? And that means to say, that's equal to say, if this machine can accept this specific string or not, something very similar, okay? And that would be something similar. Look at that. Oh my God. By coding natural numbers as a string. So how we can calculate the things with the number? So that's so easy. So if we code the natural numbers as strings, say for example, n number of a's represent the number a. For example, this can represent 3. This can represent 5. So what does it mean? So if that's the string we have, and if that's the string we have at the end of the day, what does it mean? 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 1, 2, 3, 4, 5. 3 plus 5. Yes, you can have a string like that on the head of your machine. And if you get this string and you halt when you are somewhere like a blank, that means you are doing the summation. Interesting. You are doing the summation. So we can then ask whether functions such as fx is equal to x2 or fx is equal to x factorial are computable by Turing machine. You see, that's the course computability and complexity. We wanted to know if there are machines to compute something for us or not. So we get to that point. So in the Turing machine, you can ask, is it computable, this function, this algorithm, this problem with this machine, with this Turing machine? That's the thing we want to talk about. So most of the functions ordinarily encountered are computable. Yeah, that's a very good news. So most of the functions like this are computable by the Turing. Functions which are computable by Turing machines are called partial recursive functions. Very interesting. So the functions, so the question would be, I can ask you, is this function partial recursive function? So that's exactly similar to asking that question. If this function is computable by this Turing machine, so you can look at that.